All right, now this is the part two. So in the first part, we have seen substantially the inhomogeneous Helmholtz differential equation, where we have seen that the solution is characterized by the homogeneous and the particular integral. The homogeneous right now it is represented by a product of two functions that suitably combined inside the differential equation carried out the expression on the right side here. That expression can be represented by the sum of two differential equations that suitably solve that return the homogeneous solution like this expression, where V sorry, over sine is characterized by a relation of the Vxy function determined in the middle point of the tactile related to the product of the sine function on the bottom, on the denominator. The particular integral instead is characterized by the sum of two functions, respectively in x and y variable, that return basically two differential equations that give you substantially the solution in xw and yw on the right side. So this one generated a particular solution that suitably gathered in a common coefficients as a function of f of x, gy, determining substantially the total solution for what concerns the inhomogeneous differential equation of Helmholtz. Now, by having this expression, the phi xy, we can carry out directly the current density along x and the y direction. As you can see in the expression here, have been reported all the coefficients as depicted in the coefficient alpha and gamma, epsilon, and delta. By solving this, by putting in an explicit form the current density, have been carried out 8 different components of the current density in order to understand the pattern of the current in the tactile when the AC magnetic field is acting on it. And as we can see, it's possible to see that in the 0, 0, Jx results positive as this vector. In the 8, 0, it results also positive, as you can see. Then it turns the x along AB, right here, it becomes negative, and also in 0b, become negative. Along the y direction, we have in 0, 0, directly in opposite direction of y. And in 0b, here, is directly substantially also in the negative, along the negative direction. In A0 and AB, instead, they are directly in opposite direction, which means that every time that we have a magnetic field acting orthogonally to the plane, the current turns in this sense. Now that we have the component, and we have also the coefficient in a symbolic way, not really completely known, because this is what we have to determine as a parameter identification, we can say that in a general expression of the current density is the expression right here, which is a complex function. Now, it is characterized by the magnetic field, the electromagnetic property, by the geometry, through the phasor e to the minus j pi 4, and with the geometrical parameter and depending on the time. By having this expression, it's very easy at this point to calculate the voltage of each single PN junction, because this can be carried out by differentiating towards time and the electrical field component along EX. And I'm taking only EX because the wire is connected along the X direction, not in the Y. There is not any conduction along the Y direction, unless that one related to the plate. So once we obtain the component of the electrical field along the X direction, which is this expression, we integrate towards the delta L, which is the delta X of the component, in order to carry out the voltage. And since we have a 127 PN junction plus one couple, which is characterized by the two copper plates that are connected to the red and black wire, we have substantially the voltage carried out from each single angular position. We have identified the parameter G as 9.203 for 0-degree inclination, where I remember, let me remember you that the G parameter is this one right here, which appears to be right here and right here and all over. So once you have this one, you can carry out also the other parameter, but this is an exercise for you. I have already done and I know what the values are. But the most important thing that we can say is that Behind the value that are carried out by rotating this signal, which are characterized, for example, by 0 when the plate is 90 degrees, or rather parallel to the flow of the magnetic field. As a matter of fact, it's 10 to the minus 9 compared to the 10 minus 3, while this parameter instead, this plot, shows that at the 135 we have the same amplitude of oscillation that we have at the 45 degrees, and 180 degree has the same amplitude of oscillations when we have R0 degrees. This is the best part of this study, that the current density not only is generated by the gradient voltage and by the gradient temperature, but also by the active magnetic field on it. This component tells us that basically that we're going to obtain a current density by having an alternating magnetic field with a certain frequency in presence of a particular conduction material. How can we call this? Barbaraci law? Well, I don't care as long as it exists, but it's fine to do that. All right. Do you have any questions? Because now come with the hand. I'm very happy to terminate this presentation. I hope that your curiosity has been pulled up, and I look forward to see your comment. And if you have any questions, please do not hesitate to contact me. My email is very clear on my YouTube channel. If you don't see it, just call me, send me a message, and I'll be more glad to show you any characteristic of my study. Thank you so very much, guys, and have a good day. See ya. I would like to take this opportunity to forward my special thanks to Lab Center by providing me a sponsorship in using the PCB design software Proteus, a very powerful platform in a digital sense, in order to perform and manufacture and design in a very professional manner the printed circuit board of every kind of electronic component. If you connect to the website labcenter.com/PCB, you will see tons of tutorials and designs and how to solve many problems that I'm quite sure you're going to encounter during the preparation of the PCB. This software is so famous that it's used by famous institutions such as Royal Navy, Continental, University of Southern California, Lockheed Martin, and some other university, and he provided tons of tutorial and also suggestions on how to perform at the best way your design. From the PCB design section, you will see a lot of useful information like that one that I've been looking right now. You have a different possibility to purchase this package like a perpetual license or annual license, and then depending on the package the price can vary. You have also the circuit simulation window that allows you also to perform a very accurate analysis of the electronic circuit. You can also edit, import, and also upload code in a different language. What can I say? Is one of the best software you can find in the market, and I've been using this software for 10 years. You will see this one in my next videos where we're going to perform the deck flight controller of a drone having a variable geometry structure. All right, guys, thank you so much. I hope you enjoyed, and let me know in the comments if you like this video. And if you have some questions, please do not hesitate to call me. As I said, my name is Gabriele, and I'm pleased to have show you my presentation today. Bye and have a good day.